Welcome! In this session, we'll explore the problem maximum subarray sum with one deletion. This is a fascinating problem that blends dynamic programming with optimization techniques. Stick around as we break it down step by step. The problem we're tackling here is called maximum subarray sum with one deletion. You're given an integer array called ARR, which contains at least one element. Your task is to find the maximum sum of a non-empty subarray from this array, but with one twist: you're allowed to delete at most one element from the subarray. Now, let's clarify what we mean by a subarray. It's simply a contiguous portion of the array, meaning the elements must be adjacent. For the input format, you'll receive an integer array ARR of length n, and the output will be a single integer representing the maximum sum of any subarray after potentially deleting one element. Let's look at an example to understand this better. If the input array is 1, minus 2, 0, 3, the maximum sum you can achieve is 4. Here's how we arrive at that result. First, consider the entire array 1, minus 2, 0, 3. If we don't delete any elements, the sum of the subarray is 2. However, if we delete the -2, the subarray becomes 1, 0, 3, and now the sum increases to 4, which is greater. This sum of 4 is the best possible result for this input. Let's look at another example. If the input array is 1, minus 2, 3, the maximum sum is 3. Here, the subarray 1, minus 2, 3 initially has a sum of 0. Deleting one of the -2s results in 1, minus 2, 3, with a sum of 2. If we delete both -2s, we get 1, 3, with a sum of 4. However, since we're only allowed to delete one element, the maximum sum we can achieve is 3. Now, consider the case where the input array is -1, minus 1, minus 1, minus 1. In this scenario, no matter which element you delete, the sum of any subarray remains -1, because all the elements are equal and negative. Therefore, the maximum possible sum for this input is simply -1. Let's also review the constraints for this problem. The array length can range from 1 to 100,000, and each element in the array can have a value between -10,000 and 10,000. These constraints mean your solution needs to be efficient to handle large inputs. Additionally, there are some key edge cases to consider, such as arrays with all negative values, all positive values, or arrays with only one element. For arrays with all negative values, like -5, -6, -7, the best you can do is take the largest single element, as deleting any single value won't improve the sum. On the other hand, if the array contains all positive values, such as 3, 5, 7, there's no need to delete any elements. The maximum subarray sum is simply the sum of the entire array. If the array contains only one element, for example, 10, the result is just that element itself, as there's no option to delete anything. Finally, arrays with alternating positive and negative values, like 10, -5, 10, can benefit from strategically deleting negative values to maximize the sum. This variety of cases highlights the importance of carefully considering when and where to delete an element to achieve the optimal result. To tackle this problem, we explored several approaches. The first idea is the brute force method. Here, the intuition is simple: evaluate all possible subarrays, including those formed by deleting one element. For each subarray, compute the sum and track the maximum. This involves iterating through all possible starting and ending indices of subarrays, and for each subarray, trying out the effect of removing one element. While this approach is straightforward and easy to implement, it is computationally expensive. The time complexity is O(n cubed), which makes it impractical for larger inputs. This inefficiency arises from the nested loops required to calculate all subarrays, combined with an additional loop to handle deletions. While it might be a good starting point to understand the problem, it's clear that a more efficient strategy is necessary. This brings us to the optimized dynamic programming approach. Here, the main idea is to avoid explicitly evaluating every possible subarray. Instead, we can use dynamic programming to track optimal subarray sums in two distinct states. The first state, dp_no_del I, represents the maximum subarray sum ending at index I without any deletions. The second state, dp_with_del I, represents the maximum subarray sum ending at I where one deletion has occurred. This shift in perspective allows us to simplify the problem and focus on maintaining these two states as we iterate through the array. The dynamic programming approach builds on these two states with clear recurrence relations. For dp_no_del I, we compute the maximum of extending the previous subarray sum, dp_no_del I1 plus arr I, or starting fresh with just the current element, arr I. This ensures that we always track the best sum ending at index I without any deletions. For dp_with_del I, we consider two possibilities: either extend the subarray where a deletion has already occurred, dp_with_del I1 plus arr I, or delete the current element, effectively transitioning from the no deletion state of the previous index, dp_no_del I1. These recurrence relations ensure that the values at each step are computed efficiently. Once we've processed the entire array, the solution is simply the maximum value across all indices in both dp_no_del and dp_with_del. This approach is highly efficient, with a time complexity of O(n), since we only traverse the array once, and the space requirement is constant. However, it does require careful handling of the two states, which might make the logic feel less intuitive compared to brute force. Still, this method is robust and accounts for all edge cases, such as arrays with negative numbers. An alternative to dynamic programming is the sliding window approach, which iteratively maintains the subarray sums while dynamically considering the deletion of one element. The intuition here is to reduce the problem space even further by leveraging the idea of a moving window to track sums. However, this approach is less structured and can be challenging to implement correctly. The complexity remains O(n), similar to dynamic programming, but sliding window solutions often struggle with edge cases, such as arrays filled with negative numbers or scenarios where deletions must occur outside the window. In light of these limitations, dynamic programming stands out as the more reliable method for solving this problem. It provides a structured way to account for both states, subarrays with and without deletions, while guaranteeing correctness. The key insight is recognizing that the problem can be naturally divided into these two states, and the recurrence relations handle their transitions seamlessly. This realization eliminates the inefficiencies of brute force and the potential pitfalls of sliding window techniques. In conclusion, dynamic programming emerges as the optimal approach for this problem. Its structured framework ensures clarity and correctness while efficiently handling edge cases such as arrays with all negative numbers. By breaking the problem into two states, subarrays with and without deletions, it becomes possible to compute the solution in linear time and constant space. This combination of efficiency, robustness, and scalability makes dynamic programming the ideal strategy for solving this problem. In this problem, we are tasked with finding the maximum sum of any subarray, with the added flexibility of being allowed to delete at most one element from the subarray. This additional condition allows us to handle scenarios where a single negative value may drastically reduce the overall sum. To solve this, we use a dynamic programming approach, where we maintain two key states for each index in the array. The first state, max_ending_here, I, represents the maximum subarray sum ending at index I without any deletions. The second state, max_ending_here_ with deletion, I, accounts for the case where we are allowed to delete at most one element. Together, these states help us efficiently calculate the maximum subarray sum while considering the deletion condition. We begin by initializing two arrays, max_ending_here and max_ending_here_ with deletion, each of size n, where n is the length of the input array. The first state, max_ending_here, 0, is initialized as the first element of the array, since the maximum sum ending at the first position is simply the element itself. Meanwhile, max_ending_here_ with deletion, 0, is set to 0 because no deletion is possible at the first index. Additionally, we initialize a variable max_sum to track the global maximum sum. As we iterate through the array from index 1 to n1, we update these states. For max_ending_here, I, we compute the maximum between starting a new subarray at index I or extending the subarray ending at I1. Similarly, for the second state, we consider two cases, either deleting the current element or keeping the current element while deleting an earlier one. After updating both states, we ensure that max_sum reflects the highest value among these states at every step. Once the iteration is complete, the variable max underscore sum will hold the maximum subarray sum with at most one deletion. This approach leverages dynamic programming to store intermediate results, allowing us to avoid redundant computations and achieve a time complexity of O(n). The second state, max underscore ending underscore here underscore with underscore deletion, is particularly crucial as it gives us the flexibility to improve the subarray sum by removing a single element. This could be a significantly negative number or even a smaller positive number in certain cases. For edge cases, such as when the array contains only one element, the result is simply that element, since no deletion is possible. Similarly, if all elements in the array are negative, the result is the largest single element, as removing all others would not improve the sum. To implement this solution, we primarily rely on two arrays, max underscore ending underscore here and max underscore ending underscore here underscore with underscore deletion. These store the intermediate results for the dynamic programming states, and each requires O(n) space. Additionally, the variable max underscore sum is used to track the global maximum efficiently as we iterate. The time complexity of the algorithm is O(n), as we process each element of the array in constant time. While the space complexity is O(n), due to the two arrays, it is possible to optimize this to O(1) by reusing variables, though this might come at the cost of reduced clarity in the logic. To better understand the algorithm, let's walk through an example with the input array 1, 2, 0, 3. Initially, we set max underscore ending underscore here equals 1, 0, 0, 0, max underscore ending underscore here underscore with underscore deletion equals 0, 0, 0, 0, and max underscore sum equals 1. At index 1, we compute max underscore ending underscore here 1 as the maximum of -2 and 1 plus -2, yielding -1. For max underscore ending underscore here underscore with underscore deletion 1, we evaluate skipping the current element and keeping the maximum sum of the previous subarray, resulting in 1. The global max underscore sum remains 1. At index 2, we update max underscore ending underscore here 2 to 0 and find that max underscore ending underscore here underscore with underscore deletion 2 also evaluates to 1. Finally, at index 3, max underscore ending underscore here 3 becomes 3, while max underscore ending underscore here underscore with underscore deletion 3 reaches 4 by adding the current value to the second state from the previous index. The global max underscore sum is updated to 4. The final result for this example is max underscore sum equals 4. This represents the maximum subarray sum with at most one deletion. The algorithm demonstrates how dynamic programming allows us to efficiently calculate the result by breaking the problem into overlapping subproblems. By considering both potential subarray sums, with and without a deletion, we ensure that we explore all possible options while maintaining optimal performance. This flexibility is key to solving the problem effectively. Here, we begin by defining the maximum sum method inside our solution class. The first step is to calculate the length of the input array ARR. Now, if the array contains only one element, the function directly returns that element as the result since no subarray computation or deletion is needed. Next, we create two arrays to track the maximum subarray sums. The first array, max underscore end underscore here, will store the maximum subarray sum ending at each index without any deletions, while the second array, max underscore end underscore here underscore with underscore delete, will store the maximum subarray sum ending at each index with one deletion allowed. Both arrays are initialized to 0 for all indices. The first element of max underscore end underscore here is set to the first element of the array, as the sum ending at the first index must include only that element. Meanwhile, the first position of max underscore end underscore here underscore with underscore delete is set to 0 since no deletions can occur at the start. We also initialize a variable max underscore sum to the first element of the array, which will track the global maximum subarray sum as we iterate through ARR. Then, we enter a loop starting from index 1 and calculate the maximum subarray sums for each position. For max underscore end underscore here, we take the maximum of either extending the previous subarray sum with the current element or starting fresh with the current element. For max underscore end underscore here underscore with underscore delete, we consider two cases, either skip the current element entirely or extend the subarray with a previous deletion. At each step, we compare and update the global maximum, max underscore sum, to ensure it always holds the highest subarray sum encountered so far. Finally, once the loop is complete and all indices of the array have been processed, the function simply returns the value of max_sum. This value represents the maximum subarray sum that can be achieved either with or without one deletion. By efficiently combining dynamic programming and careful bookkeeping, the algorithm ensures an optimal solution in linear time. Here, we are implementing the solution for the problem in Java. The function maximum_sum starts by checking an edge case. If the array has only one element, we simply return that element because there's no room for deletion. Next, we define two arrays, maxEndHere and maxEndHere with delete. The first array, maxEndHere, keeps track of the maximum subarray sum ending at each index without any deletions, while maxEndHere with delete stores the maximum subarray sum ending at each index when we are allowed to delete one element. We initialize the first element of maxEndHere with the first element of the input array since no deletions are made initially, and we set the first element of maxEndHere with delete to 0 because deletion isn't possible at the start of the array. We also initialize the variable maxSum to the first element of the array to track the global maximum sum as we iterate through the array. Now, using a loop from index 1 to the end of the array, we update maxEndHere at each step by taking the maximum of the sum of the current element with the previous subarray sum, or just the current element itself. This ensures we're always considering the most optimal subarray ending at that point without any deletions. For the maxEndHere with delete array, we calculate the maximum subarray sum at each index when one deletion is allowed. Here, we take the maximum of two possibilities: either we skip the current element by continuing from the previous subarray sum in maxEndHere, or we include the current element by adding it to the previous subarray sum in maxEndHere with delete. This way, we account for both cases where the deletion has already occurred or is about to occur. After calculating these values at each index, we update the maxSum variable to the maximum of its current value, maxEndHere, I, and maxEndHere with delete, I. Finally, after iterating through the entire array, we return maxSum as the result, which represents the maximum subarray sum with at most one deletion. In this example, we are given the array 1, -2, 0, 3. First, we initialize our variables, n is set to 4, and we create two arrays, max_end_here and max_end_here_ with _delete, both initialized to 0. The variable max_sum starts with the first element, which is 1. Now, in the first iteration, when I equals 1 and arr, I, is -2, we calculate max_end_here, 1, as the maximum of max_end_here, 0, plus arr, 1, or simply arr, 1. This gives us -1. For max_end_here_ with _delete, 1, we take the maximum of max_end_here, 0, and max_end_here_ with _delete, 0, plus arr, 1, resulting in 1. The max_sum is then updated to the highest value among max_sum, max_end_here, 1, and max_end_here_ with _delete, 1, which keeps it at 1. Moving to I equals 2 with arr, I, as 0, max_end_here, 2, becomes 0 because we calculate the maximum of -1 plus 0 and 0. For max_end_here_ with _delete, 2, we again find the maximum, which results in 1. The max_sum remains unchanged at 1. At I equals 3, when the array element is 3, we calculate max_end_here, 3. Adding max_end_here, 2, to arr, 3, gives us 3, which is greater than arr, 3, alone. Similarly, max_end_here_ with _delete, 3, is calculated by taking the maximum of max_end_here, 2, and max_end_here_ with _delete, 2, plus arr, 3, resulting in 4. Now, max_sum is updated to the highest value among the current max_sum, max_end_here, 3, and max_end_here_ with _delete, 3, which is now 4. This concludes the first example where no deletion was needed, and the output is 4. Now, let's examine the array 1, -2, 3, -4, 5, where a single deletion may be necessary. We initialize our variables, n becomes 5, while max_end_here and max_end_here_ with _delete are arrays of zeros. The max_sum starts as 1, the first element of the array. For I equals 1, the element is -2. We calculate max underscore end underscore here, 1, as -1, and max underscore end underscore here underscore with underscore delete, 1, remains 1. The max underscore sum stays at 1. When I equals 2, the element is 3. We calculate max underscore end underscore here, 2, as the maximum of adding max underscore end underscore here, 1, to 3 or just 3, which gives us 3. For max underscore end underscore here underscore with underscore delete, 2, we consider the maximum of max underscore end underscore here, 1, and max underscore end underscore here underscore with underscore delete, 1, plus 3, resulting in 4. Here, max underscore sum updates to 4. At I equals 3, the value of ARR, I, is -4. We calculate max underscore end underscore here, 3, as -1 and max underscore end underscore here underscore with underscore delete, 3, as 4, showing that deleting -4 can preserve the higher running sum. The max underscore sum remains 4. Finally, at I equals 4, with ARR, I, as 5, max underscore end underscore here, 4, becomes 5, and max underscore end underscore here underscore with underscore delete, 4, calculates to 9 by adding 5 to max underscore end underscore here underscore with underscore delete, 3. The max underscore sum now updates to 9, which is the output for this example. In the third example, the array consists entirely of negative numbers, -1, -2, -3, -4. Here, we initialize n as 4, and both max underscore end underscore here and max underscore end underscore here underscore with underscore delete as arrays of zeros. The max underscore sum starts at -1, the first element. At I equals 1, with ARR, I, as -2, we calculate max underscore end underscore here, 1, as -2, and max underscore end underscore here underscore with underscore delete, 1, remains -1. The max underscore sum stays at -1 because it is the highest value among the three. For I equals 2, with ARR, I, as -3, max underscore end underscore here, 2, becomes -3. Max underscore end underscore here underscore with underscore delete, 2, is calculated as -2, by comparing -2 and -4. The max underscore sum remains unchanged at -1, as it is still the largest value. Finally, at I equals 3, where the array element is -4, max underscore end underscore here, 3, becomes -4. Meanwhile, max underscore end underscore here underscore with underscore delete, 3, is calculated as -3, which is the result of taking the maximum of max underscore end underscore here, 2, and adding ARR, 3, to max underscore end underscore here underscore with underscore delete, 2. The max underscore sum remains -1, as it is the highest value encountered throughout the array. This output of -1 makes sense because, in the case of all negative numbers, the largest sum is simply the least negative single element. This concludes the walkthrough of the third example, showing how the algorithm handles arrays with exclusively negative elements. The time complexity of the algorithm is linear because it processes the input array in a single pass. First, we allocate two auxiliary arrays, max underscore end underscore here and max underscore end underscore here underscore with underscore delete, each of size n, which requires n time. Initializing these arrays and a few variables, such as max underscore sum, is a constant time operation. Next, the main computation happens in a single for loop that iterates through the array from index 1 to n1. During each iteration, we calculate max underscore end underscore here, I, and max underscore end underscore here underscore with underscore delete, I, using a constant number of operations, both of which are 1. Updating the maximum result at each step using the max function is also 1. Since the loop runs n times, the total time spent on these operations is n. Finally, returning the max underscore sum at the end is an 1 operation. Altogether, the algorithm achieves a time complexity of n. The overall time complexity is dictated by the single traversal of the array, making it n. Now, let's analyze the space complexity. The algorithm uses additional memory to store intermediate results in two auxiliary arrays, max underscore end underscore here and max underscore end underscore here underscore with underscore delete, which take n space each. Beyond these arrays, a few variables are used, including max underscore sum, the array size n, and loop control variables, all of which require 1 space. When we combine the space used by the arrays and the variables, the total space complexity becomes n, dominated by the two auxiliary arrays. This balance of linear time and space complexity is what makes this solution efficient. To better understand the efficiency of this approach, let's compare it to a naive solution. A naive algorithm would generate all possible subarrays, including those that allow one deletion, to compute the maximum sum. Generating all subarrays requires n superscript 2 time, and for each subarray, summing up the elements could take an additional n in the worst case, resulting in a total time complexity of n superscript 3. In contrast, the optimized solution leverages dynamic programming to avoid redundant computations. By storing intermediate results in two auxiliary arrays and updating values in linear time, the optimized algorithm reduces the time complexity to n. The space complexity also stays at n, thanks to the use of only two arrays and a few extra variables. This significant improvement makes the optimized solution far more practical for large inputs. Let's break down the algorithm's performance under different scenarios. In the best case, where all elements in the array are non-negative, the algorithm still needs to process the entire array to ensure correctness, resulting in a time complexity of n. For an average input containing a mix of positive and negative values, the complexity remains n, since the algorithm performs the same operations regardless of the input distribution. Even in the worst case, where all elements are negative, the algorithm behaves consistently, iterating through the array once and maintaining n complexity. Mathematically, the time complexity is derived from the fact that each iteration involves a constant amount of work, repeating n times for a total of n. Similarly, the space complexity is determined by the two auxiliary arrays of size n, leading to n space usage. For example, if the input size is 100, the memory usage grows linearly, storing two arrays of size 100. This linear time and space complexity demonstrates that the algorithm is well suited for this problem and achieves optimal performance. When approaching this problem, there are several common mistakes you'll want to avoid. One major pitfall is not handling edge cases properly. For instance, if the array has only one element, contains all negative elements, or is even empty, these scenarios can produce incorrect results if not explicitly accounted for. Boundary conditions like these should always be tested. Another frequent error comes from incorrectly calculating subarray bounds. This often happens when working with sliding window or iterative approaches, where off-by-one errors can sneak in due to mismanaged loop conditions or array indexing. It's also important to avoid overcomplicating the problem. Some beginners try to compute the deletion and the subarray sum in a single step, which introduces unnecessary complexity. Instead, break the problem into smaller, manageable parts. Additionally, brute force implementations, while simple conceptually, often become infeasible for larger arrays. For example, recalculating subarray sums repeatedly can lead to n cubed time complexity, which is far from optimal. Finally, many overlook the efficiency of prefix sums. By pre-computing cumulative sums, you can avoid redundant calculations and significantly simplify your solution. Always consider whether prefix sums could enhance your approach to problems like this one. Now, let's focus on insights that can help you stand out in interviews. Recognizing patterns in array problems is crucial. Many revolve around tracking subarrays or subsets. Techniques like the sliding window, prefix sums, or dynamic programming often provide the best solutions, so being able to identify when to apply them is key. When optimizing, start with brute force to fully understand the problem, but quickly transition to more efficient methods. Explaining your thought process as you refine your approach is something interviewers value highly. Communication is also critical. Explicitly discussing edge cases and test scenarios demonstrates thoroughness. For example, asking, "What happens if all elements in the array are negative?" shows that you're thinking critically and preparing for all possibilities. Finally, keep in mind that this problem is closely related to others, such as LeetCode 53, which focuses on the maximum subarray problem, or LeetCode 152, which deals with the maximum product subarray. Familiarity with these related problems can deepen your understanding and allow you to draw parallels during interviews. There are also several alternative approaches to solving problems like this one, each with its own strengths and trade-offs. Sliding window techniques are particularly effective for finding contiguous subarrays, as they minimize redundancy by maintaining a running sum or product. However, they typically work best with fixed-sized windows unless you adapt the method dynamically. Prefix sums are another powerful tool. By pre-computing cumulative sums, you can reduce subarray sum calculations to 1 time. The trade-off here is the additional memory required to store the prefix array. Dynamic programming is ideal for problems that involve overlapping subproblems, such as finding the maximum subarray or the longest increasing subsequence. While highly efficient, DP solutions may require significant space for storing intermediate results. Lastly, divide-and-conquer approaches break the problem into smaller subproblems, which can be particularly useful for extending algorithms like cadans. However, this method can be more complex to implement compared to sliding window or prefix sums. Each of these approaches has its place, and understanding their trade-offs will help you choose the right tool for the problem at hand. Great work! Today, we tackled the maximum subarray sum with one deletion problem, exploring both brute force and optimized approaches. We highlighted how dynamic programming can simplify complex subarray problems while ensuring efficiency. Thanks for joining, and keep practicing. Your coding skills will only get stronger. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!